So once again we'll start with limits, fits and tolerance, a brief introduction, a brief review on what was covered in the previous class, and later on we'll continue with clearer concepts of limits, fits and tolerance, and a concept called selective assembly and interchangeability. Why selective assembly is important and how selective assembly and interchangeability is taken into account in various cases. So in the previous class we had discussed what do you mean by limits, fits and tolerance and why limits, fits and tolerance is required. So which are the, thank you sir, areas which are affected by adapting the concept of tolerance. So over here you can have a look that engineering tolerance is directly related to the product design, manufacturing as well as quality control. Quality control is nothing but inspection, and product design is the first step in creation of any new product. The second step is the manufacturing, and finally the inspection. So a good mechanical engineer should always know the concept of engineering tolerance, where to provide, how to provide, what type of system standards should be used, and so on. So basic definitions of what is basic size, limits of size, maximum minimum limits of size, hole, shaft, lower and upper deviation, grade of tolerances, etc. So a quick review again. Over here you can see a neat sketch of limits, fits and tolerance, representing the limits, fits and tolerance. We have the hole, we have the shaft, a small tolerance is provided on both shaft as well as on the hole. So with respect to this we have the minimum diameter and the maximum diameter. So with respect to the basic line, the zero line, the basic size of the zero line, we can give the upper and lower deviation for hole and shaft. So all these things were discussed in the previous class. So what is unilateral tolerance? Tolerance on one side, that is either on the positive or the negative side. Then bilateral tolerance, tolerance provided on both sides of the basic zero line. So what do you mean by fundamental deviation? The types of deviations for hole and shaft, the grades of tolerance. So we have 18 grades starting from IT0, IT01 up to IT16. So degree of error increases with the precision of the process and the size of the component. This is a point to be noted. Then we had the different class of work and processes for different grades of tolerance starting from IT1 till IT16. We had some examples. So next we had a brief introduction to the fundamental deviation, how to identify the type of fit, the fundamental deviation as well as the grade of tolerance. Over here we were discussing yesterday. So this is the sketch that represents the hole. So we have the zero line. This is the zero line representing the x-axis. Anything above it is positive and anything below it is negative. So you can see over here A has the highest deviation and H does not have any deviation in case of hole. And as you move further and further, you can see ZC, ZA, ZB, MNP, RST, UV, etc. So all these have deviations in the negative side. So similarly, a similar graph is plotted for the shaft, but all the alphabets are replaced, are interchanged. In case of positive, it is on the negative side. You can see A is at the bottom below the x-axis, then B, C, D, H again touches the zero line but from the bottom side. So over here you can see hole touches the zero line from the top side. So it is just a mirror image of the representation of hole. So whenever you want to represent tolerance you can represent using this designation, okay, similar designation. So over here you can see an example of 45H6G7. So you might have a question, sir, just by looking at this particular value H6G7, how can I say whether it's a clearance fit, interference, or a transition fit? So as discussed yesterday, Jitni sir had mentioned that anything up to H, you can say it can be a clearance fit or H. So H is basically the whole basis system, capital H, and anything before H with respect to shaft A to G will be clearance fit, and anything above after J, isn't it, sir? Yes, after J it will be interference fit. So transition fit will be usually somewhere here in between H, JS, etc. So we can we'll discuss, sir will discuss some examples with respect to interference fits at the end of this class. So over here you can see the upper and lower deviation. This is how it is represented. So A to G slightly above the X line, the 0 line. H is exactly on the 0 line. J is on both sides of the 0 line. K and till ZC you can see on the negative side for holes. And similarly for shafts, that is for external features, this is the lower deviation up till H. H is exactly on the 0 line and slightly below. This is the tolerance that we can say. And anything about this will be on the positive side. Okay, so this is the concept of upper and lower deviations. You can see these are all negative till H, and after this K till ZC, it is positive, that is on the upper side. Similarly, the vice versa in the case of holes. So fits. What do you mean by fit? When two parts are to be assembled, the relation resulting from the difference between the size before assembly is called a fit. You have a hole and a shaft. The relation between the size of hole as well as the shaft is called as the fit. A fit is usually represented by this particular designation 30 H7 G6, where H7 represents the fundamental deviation and the tolerance on the hole, and G6 represents the fundamental deviation G, and 6 represents the tolerance grade on the hole, and 30 represents the basic size. So there are different types of it. Yes, sir. Yes, sir. H7 G6.
They should be able to draw this sketch easily.
Yes, sir.
First step would be to draw the sketch, understand what kind of fit it is. So let us analyze this 30, H7 and G6. H is the hole designation, G is the shaft designation, and H means one of the fundamental deviation for hole is 0. So this is H7, okay, H hole, and this is, I can write this as IT grade 7.
Yes, sir.
This is IT grade 7, which is equal to, please let me know, later on we will write that. IT grade 7 is equal to some 16I if I am not mistaken. We will write that. That anyway we can write it. Next, this is a lower deviation of hole. This one, lower deviation of the hole. This is upper deviation, which is equal to 0. Fundamental deviation is also 0. FD is also 0 here. Then this is upper deviation of hole. Okay. Next, this is nominal size, which is 30 mm. So this is with respect to H7 hole. Once we get this, we should be able to find out how much is IT7, and that is further. Next, let us discuss about G shaft part, G6 shaft. One sec. I will write this nominal size here, 30 mm. So this is nominal diameter. G6 shaft. G in the sense A to H shafts are all below the normal line or the XY line or nominal diameter size. So that means if it is A somewhere here, G somewhere here, H is somewhere here, and beyond, this is how the shaft designation goes across. So let us call this as G shaft with IT grade of 6. G IT grade 6. What does G shaft mean? It means that it is below the normal line.
Zero line.
So we need to find out how much is this fundamental deviation. Fundamental deviation for G shaft is already designated. We can get it from
Based on the
standard table.
diameter.
Based on the diameter, we know how much is this. So this is fundamental deviation. Okay. So fundamental we will write. Question here is, sir, whether it is positive side or negative side. Let us not worry much about positive or negative. Let us bring that into our drawing itself in our mind. Now, fundamental deviation is some number.
Yes.
And it is below the nominal size, which effectively means it is minus. And if there is any shaft, let us say P shaft, Q shaft or R shaft, that would be shown somewhere here, and the fundamental deviation is positive. So if you bring this drawing in the mind, positive, negative combinations or any such disturbances, misunderstandings can be eliminated straight away. So we are not worried plus side, minus side. However, this is plus side, positive deviation for the hole, H hole. Right up till A to H, we will have positive holes, positive deviations. And for H hole and H shaft, fundamental deviation is 0. Now, there is one small deviation from this. Now let me say, if I mark this as H6, G6, H6, G6, whether my calculations will get reduced or not. What's your take on this? IT grade 6, IT grade 6. Both mean the same. IT value will remain the same. Diameter is same. So which effectively means even whether you calculate for hole or shaft, both the values will remain the same. Because it's the IT7 and IT6, the deviations will differ, but otherwise, when the grades are same and the diameter is same, obviously the tolerance is also same. Okay, that's a small deviation, change from this given problem. Now, this is upper deviation of the shaft, upper deviation for the shaft, and this value is lower deviation for shaft. So, 4 components. We need to, and given the problem, we will have the problem consists of 2 parts. One is with regard to finding out the tolerances. Next, if it is given, we need to go ahead with gauge design. Okay. Now, I will mark them as, this is number 1, number 2, number 3, and number 4. If you get 4 answers, this problem gets 4.
Yes.
How to solve that? We will discuss about that in the subsequent steps. Let us analyze what 30H7G6 means. Same is the case with the next example, whatever is given. Just show what is the
H7P6.
H7P6. Okay. So this is next one is, let us analyze this. 30H7.
Some other example. Usually that is just an example, but yes, maybe K6.
Okay. H7, obviously it means the same here as was discussed earlier. H hole, fundamental deviation for H hole is 0. K shaft. K shaft, if you please go back to that
Previous
main drawing. K shaft, can you see here? It is above the normal line or the basic line, which means that the deviation is on the positive side. So our K shaft would be somewhere. Let me draw it with another color. I can designate K shaft somewhere here.
Calculation.
I'm not sure whether K falls exactly on the line or not. I think it is above the
slightly.
So I'll show you. Please note this difference here. K shaft. So it is just above, there is some fundamental deviation. We need to identify how much this is K. Small k, K7, that means this is IT grade 7. IT grade 6, sorry. IT grade 6. And this is K sharp. Yeah.
The fundamental deviation is K.
K7. This is the fundamental deviation for K sharp. For K sharp, we will discuss that about fundamental, or we will get that from the standard table. Okay. Can you please show the standard table for fundamental deviation? Let us finish off that here as well.
I think I have it in a different
okay, that's fine.
Presentation.
Just a minute. We will have a look.
Yes, sir. So Chitnis sir has some tips.
Yeah, as far as fundamental deviation is concerned, for H shaft and H hole is 0. But for any given shaft and hole, fundamental deviation is numerically same only in opposite direction. If it is positive for hole, it is negative for shaft, same shaft. But for A to Z, whatever shafts, the International Organization for Metrology and Measurements has come up with certain standard fundamental deviations, and those fundamental deviations are based on the diameter of the hole or shaft. For example, for F shaft, sir, for F shaft, the fundamental deviation is, for F shaft, the minus 5.5 d raised to 0.41. Minus 5.5, 0.41. If it is for F hole, it will be plus 5.5 d. Huh? Yeah. If it is for hole, it is a plus 5.5 d raised to 0.41. So you need not have to remember the formula there. You have to refer to the data, or data may be given in the your numerical, and that can be definitely.
If you replace this with 4, it becomes, the answer is same but only on the
positive side. Okay. So this is how the fundamental deviation is found. But you need.
What is the fundamental of D? Please have a look with respect to this sketch. K shaft. Yeah.
K shaft will be plus
0.6 cube root of. So fundamental deviation we can always get for AFD. Fundamental deviation for K shaft is equal to. There's a special case for K for grades less than K3.
This is different.
K, it is 0. It's very minimal value. K4 to K7, 0.6 cube root of D. So our particular problem falls under K6. So it is.
Sir, D1. I will tell you what is that D1. That is not the actual diameter.
Yes.
That is not. The D1 so that 0.55 minus 0.55 D1 raised to 0.41. Okay, it is that D is not actual dimension of the workpiece, but it is the geometric mean of the steps. The sir will tell about the geometric steps at a later stage.
Discussing about the.
When we are discussing about the numerical, we will come across the diameter steps.
Just pause for a minute.
Yeah. See, there are two things that zero line we call it, but most of the industry applications say that zero line is zero deviation line. Zero line is a zero deviation line. That means if any component, say it is a 40, that means zero line represents the exactly 40 basic size. Zero line represents exact basic size, and from that the deviations are always plotted on the one side. That is what is the idea. I hope I have.
Yes, sir. Zero. Yes.
Yes. Zero line is a basic size. In short, zero line is a basic size, and tolerance chart always talks about only deviations, tolerances, and allowances, and not the absolute damage.
Thank you, sir. Yes, sir. Correct. So what do you mean by interchangeability? A very simple example that I can quote is, so whenever your ink gets over in your pen, you just say out the name and the model, the type of pen that you have, and the shopkeeper replaces with a different refill. And immediately you can replace the empty refill with a newer refill, and this concept can be said as interchangeability. So basically, interchangeability means there will be some deviation, but that is permitted. And if you want to replace a particular product with a new product, that should be within that particular tolerance. So for manufacturing a large number of components, it is economical to produce both the mating parts using the same operator or on the same machine. Further, such parts need to be manufactured within minimum possible time without compromising on quality. To enable the manufacture of identical parts, mass production, an idea of last industrial revolution that has become very popular and synonymous with the present manufacturing industry becomes inevitable. Modern production techniques require that a complete product be broken into various component parts so that the production of each part becomes an independent process, leading to specialization. The various components are manufactured in one or more batches by different persons on different machines at different locations and are then assembled at one place. To achieve this, it is essential that parts are manufactured in bulk to the desired accuracy and at the same time adhere to the limits of accuracy specified. Manufacturing of components under such conditions is called as interchangeable manufacture. When interchangeable manufacture is adopted, any one component selected at random should assemble with any other arbitrarily chosen mating component. So that is the example that we had discussed. So you can pick any refill and that refill should be suitable for that particular pen. In order to assemble with a predetermined fit, the dimensions of the components must be confined within the permissible tolerance limits. So that is about interchangeability. It also means they are identical parts manufactured by different operators using different machine tools under different environmental conditions, but can be assembled and replaced without any further modification during the assembly stage and without affecting the functioning of the component when assembled. So production on an interchangeable basis results in an increased productivity with a corresponding reduction in manufacturing cost. Another major advantage of interchangeability is the ease with which replacement of defective or worn out parts is carried out, resulting in reduced maintenance cost. So that is interchangeability. Next is selective assembly. So what do you mean by selective assembly? So many a times complete interchangeability is not possible due to the accuracy requirements. Instead, we can go for selective assembly approach. So what do you mean by selective assembly? After attaining complete interchangeability, in the case involving some extra cost in inspection and material handling, a selective assembly approach is employed wherein the parts are manufactured to wider tolerances. In selective assembly, despite being manufactured to rather wide tolerances, the parts fit and function as if they were precisely manufactured in a precision laboratory to a very close tolerance. This ensures complete protection and elimination of defective assemblies, and the matching costs are reduced because the parts are produced with wider tolerances. So the advantage over here is the tolerance can be slightly higher, but the type of fit that we get is almost similar. I hope I am right, sir. Yes, the type of fit will be consistent, but the amount of tolerance that we have is slightly bigger so that we can easily work on the products. So selective assembly usually finds application in aerospace and automobile industries. In a broader sense, a combination of both interchangeable and selective assemblies exists in modern day manufacturing industries, which help to manufacture quality products. So that is about selective assembly and interchangeability. Sir, any inputs that you want to provide for this particular topic?
Point clear on selective assembly. Yes, sir. Thank you, Nikhil. You have corrected it, saying that selective assembly gives the correct or consistent fit. And you have also mentioned that it is mostly used in aerospace and automobile industries. Now I can take the example of cylinder and piston mechanism or IC engine. Cylinder and piston mechanism or IC engine may be working with plus or minus 2 microns tolerances. In that case, manufacturing of cylinder or piston within 2 microns is not possible. It will result in larger rejects. So what they do is, cylinder is manufactured with say about 18 microns and the piston also manufactured 18 microns. But what you want only 2 microns, correct? So first, this segregate the components. Cylinders having 2 microns tolerance, they segregate. And pistons 2 microns, then they fit, so that you get. Then 2 to 4 microns, 2 to 4 microns here. Then 4 to 6, 4 to 6. So that is how they segregate with the actual dimensions of the component, and then they assemble it. This is called the selective assembly, so that the concept of selective assembly gives you the wider tolerance. At the same time, when you actually assemble, it results in minimum allowance.
So the quality of the product goes on increasing. I mean, it's consistent. So with this, I think we can start with a few numericals on limits, fits, and tolerances. I think we start using the board so that
We can close it.
yes, sir.
Let's follow it.
I have everything ready. Done that.
Thank you, Dr. Nikhil. So we will go ahead with a solution to a given numerical with regard to limits, fits, and tolerances. Let us start with an example. This was asked in VTU exam way back in 2003, probably 17 years ago, when these students were in their first standards also. So this let us solve this problem. Problem will remain more or less the same, irrespective of the year or the semester. This is a problem 50 mm, nominal size is 50 mm, and this is H7D8. Yeah. Given numerical is (50 H7D8). Question is, find the hole and shaft dimensions with following given data. Data is diameter of step sometime could be given, may not be. It is not very sure that the diameter of step could be given in the examination. He has provided here 30 to 50 range. This is dia step 30 to 50. First information. Fundamental deviation for D shaft has been given. FD for D shaft minus 16D to the power 0.44 minus minus 16D to the power 0.44. Okay. Next, fundamental the tolerance value I, third one, I equals 0.45 cube root of D plus 0.001 D. Next, fourth value that is given is IT tolerance grade IT6 equals 10I. Above IT6 grade, see we have one more, IT7, right? IT7 has not been given, but it is mentioned that above IT6 grade, tolerance is multiplied by 10 at the every step of fifth step. I repeat, after IT6 grade, tolerance is multiplied by 10 at each of fifth step. It could be given straight away, but here it is indirectly given. Yes, H7D8. But he has given this information. It could be an additional information to create the. Yeah.
And how to get that integrated there?
Yeah, that we can do. Two things here. Above IT, we need to have IT6, IT7. We need to have IT8, and what is given to us is the value of only IT6. We don't have 7 and 8.
IT8 is 55.
Yes. Straight away we can get it from the tables. If you remember, we can use it, but he has given in this case a specific case. Okay. We can go ahead with IT7. Straight away IT8. 25. Right? We can give that. IT8 25i, IT6. We will change this. IT7. How much is IT7? 16i. IT7 16i. IT8. That's it. So this is what is the given data. Now let us analyze the problem. Before solving the problem, let us analyze what has been given. First step would be to draw the sketch. This is H7D8. H7. This is IT grade 7, which is equal to this is IT7, that's equals 16i. Okay, next, this is nominal size, which is 50 mm, nominal diameter. Unless otherwise specified, all the dimensions are in mm. Next, this is D shaft, D8. This is IT8, IT8. That's equals 25i. Okay. This is fundamental deviation for the shaft, FD, shaft for D shaft, which is equal to minus 16d to the power 0.44. Okay. So these are the things that we need to find out. Let us know what are the values. Let me number them, what we need to find out. One is minimum size of the hole. Minimum size of hole. Next, second, maximum size of hole. Right? Next, number 3. Maximum size of the shaft. Then number 4, last one, minimum size of the shaft. Now, let's also understand one concept that was not discussed yesterday and today. Maximum size and minimum size of the hole and the shaft. Look, when you consider perspective, this is the minimum size of the hole in the sense A hole manufactured below this line, below nominal size. Say if it is 50 mm, if we make a hole of 48 mm, let us for example 49 mm. Two questions. One, can it be accepted? Obviously not. It is not adhering to the standards. It should be 50 mm H7. Fine, it gets rejected. Second question, can we still consider it for manufacturing with some modification? Can you do it or not? Obviously we can do. We can enlarge the hole size, make it into 50 and still use it when the tolerance levels are reached. This is what I mean here. This is already 40 mm, this is 50 mm, this is let us say 51 mm. So this is the minimum size of the hole, this is the maximum size of the hole. Next small corollary, if some hole is given as 51 by chance, obviously it gets rejected. Now, can it be considered for manufacturing or remachining and then use it in the assembly? Obviously not, it is not possible. Hole size is already beyond the maximum size, we cannot reuse it, remachine it, do anything is not possible. It has to be rejected. If the value is something less than this is within the acceptable zones. Anything less than this, we can send it back to machining operations, enlarge the hole and use it. It involves an additional cost, that's separate part. Next, exactly opposite is with respect to shaft. What is the maximum shaft? See, this is the maximum material for a shaft, this is the minimum material for the shaft. If the shaft is anything less than this, we cannot add any material to the shaft and reuse it. It is not possible. If by chance you get a shaft which is bigger, one thing it gets rejected no doubt, but we can still work on that. We can send it back to the machining and we can use it if the tolerance level is within these two zones. But if the given shaft is less than the smallest allowable size, obviously it goes for rejection. So this is maximum metal condition and minimum metal condition for hole and the shaft needs to be borne in mind. Smaller holes can be enlarged, fine, they can be reused. But a larger hole if they are given, so they go for rejection. Larger shaft, bigger shaft, if more than allowable size, it is initially rejected but it can be reworked and it can be put in use. But if the shaft size given is smaller than the smallest allowable size, obviously the shaft gets rejected. It's a huge expense to the industry. So our concern is always to see that rejections reduce and always we manufacture the components for the within tolerance zones, allowable tolerance zones. Okay, coming back to this numerical. So these are the four things that we need to calculate. One, maximum size of the hole. Second, minimum size of the hole. Third, maximum size of the shaft. This is the maximum size of the shaft. Fourth, minimum size of the shaft. Please note students, this is only the 50% of the numerical. It is right at the beginning, it is given only for hole and shaft design. But the problem can as well be asked, design go and no-go gauges, that we will discuss in our further classes, go and no-go gauges. In that case, we need to design go and no-go gauges, go gauge for hole, no-go gauge for hole, go gauge for shaft, no-go gauge for shaft. For go, you have two values, minimum go value, maximum. Next, we have to add the tolerances, wear allowance, then again no-go zone we have to find out. So four values for holes, go and no-go, go two values, no-go two values. So four values here, another four values here. So effectively 4 plus 4, 8 and earlier 4. We need to find out 12 values if this numerical has to be completed in all respects. But that is not asked at the moment. We'll go ahead with only the solution for hole and the shaft. I think the problem is clear. Can we go ahead with the solution or we should try tomorrow? We should wind up now and try to go ahead with the solution by tomorrow. Let me review the given problem. Okay. Any given problem for that matter is of this category or specification. Some of these could be given. One more thing, diametral step. I forgot to mention about this. There are standard diametral steps mentioned. Those diametral steps are 1 to 3, 3 to 6, 1 to 3, 3 to 6, 6 to 9, 9 to 18, 18 to 30, 30 to 50, 50 to 80, 80 to 120, 120 to 150 and 150 to 300, 300 to 500. So these are the standard diametral steps recommended. Please note, students, it could be given in the exam, the standard diameter step, or it may not be given. We cannot assume that it will be given in the examination, so we need to keep in our minds 1 to 3, 3 to 6, 6 to 9, 9 to 18, 18 to 30, 30 to 50, 50 to 80, 80 to 120, 120 to 150, and the next last is 150 to 300. Then the lastmost step, if I'm not mistaken, is 300 to 500. And why it is given only 500 is 500 mm diameter hole and the shaft is normally the working range of any manufacturing machine tool industry or manufacturing industry, unless otherwise there are some specific requirements to go beyond 500 mm or 50 mm hole in the shaft, 50 centimeter hole in the shaft. Okay, this is covered. Next, diameter step is over. Hole, for each hole, the fundamental deviation is 0, so that's why you don't get, look, fundamental deviation for shaft is given, you are not given with the fundamental deviation for hole primarily because each hole has 0. Had it been, say, let us say, F, if this were to be F hole, F7, F5, F8, whatever is the value, we would have been given with the fundamental deviation for F hole. That will be given in the examination. But present, and most of the numericals will have H because standard practice is to go for hole based system, and one of the deviation for holes is 0. Fundamental deviation is 0. Next, now I come to this very important part. This part, I is 0.45. How to find out this D? This is, D is found out by finding out the diametral step root of D1 into D2. Root of D1 into D2. There are slight confusions being created here by while substituting in microns and millimeters. Please note, D value is always in terms of millimeters. Both D1 and D2 are nothing but diameter steps. D1, next, this is D2. And both are in mm. Obviously, you get the value of D in mm. D value is in mm. Next, we need to find out tolerance value I. I is given as 0.45 cube root of D, 0.001 D. There are two things important. What is the value of D to be substituted? What is the answer that we get across? Please note, D is to be substituted in mm. Always the normal average diameter D is given in terms of, is used in terms of millimeters, but answer I you get in microns. Please note this. That is nothing but 0.001 mm. And this is exactly where many students make a mistake. They convert this in millimeters or microns, substitute in microns, convert this or get this answers in terms of millimeters, which is wrong, or vice versa, convert everything in millimeters and find out this as my millimeter, again that is wrong. Please note, the only standard procedure is D value, whatever you get in the previous step, substitute the D here. Straight away, I is equal to 0.45 cube root of D 001 D, and keep in mind the answer you get is in micron. Substitute in terms of microns. Later on, you can convert it in terms of millimeters. If you follow this step, this thing will be of great help and used to us for during our further numericals or calculations. Okay, once you get this, we can find out how much is IT7. 16I, we can find out. Then IT8, 25I, we can find out these two values. So, with this, we should be able to solve the problem relatively easier. Make sure about the units, make sure about the procedure. Let us all meet in our next class. Thank you all. Have a nice day. Thanks to Dr. Nikhil, thanks to Professor Chitnis for joining this session and giving their valuable inputs. And we will also continue with our regular classes in the next video that we are going to post. Thanks a lot.